Okay, Ramesh, you showed me what UART looks like on the line, but can you show me how it works internally inside the UART device?
So we said there's a line that connects two microcontrollers, let's say, or a device. And now we saw what happens here. So we want to see what happens inside the
Yeah.
microcontroller. So inside the microcontroller, we have a module called the UART module, whether it's transmitting or receiving. This is on the receive side, this is on the transmit side, but it doesn't matter. So we'll look at what happens internally. So in a nutshell, what should happen is this line here is connected to something, right? What is it connected to? As it turns out, it's connected to a shift register.
Oh. So what's a shift register?
A shift register is where bits move out that way, the next bit moves in that way, the next bit moves in that way, all the way till the very end. So this is the bit that goes first on the line, and this line, and so on. And there's a clock that controls it.
Now, you saw in the last video that the frame contained a stop, data, and a start that was 10 bits wide.
Yeah. So this shift register has right now the start bit here and the stop bit here.
Okay, so it's also 10 bits wide.
Yeah. And this is where our payload, which is the 8 bytes, are sitting. So how did they get there?
Ooh.
Well, they got there by another buffer, if you will. That's what is called it's 4-element deep, so it's a 4-element buffer, which is a FIFO.
Ooh.
A first in, first out.
All right.
So we're going to put things into it, and as things are added to it, they go into that shift register and they get out. Right? That's 4-element deep. Now this register will, on the transmit side, it's called a transmit data register, intuitive enough.
And what does my software do?
So on the software, I have to write to this register, but before I write to that register, I want to make sure that there is room for data to go into this buffer. So the transmission looks very simple. It says there is a flag here, which is the transmit FIFO full register. If it's full, I'm not going to write.
Oh, yeah, because you just wasted.
Yeah, so I'm going to check if that flag is set. It means that it's 1.
Okay.
If it's 1, I'm going to go back.
Okay, got it.
If it's 0, then I can write. So I'm going to put my data, my TX data gets the data.
All right.
We'll write the data to it. And that's our transmission. That's as simple as it is. Now on the receiver side, we have to have something else that's similar to this, right? Ooh. So there must be a receiving. This guy comes in. We have another register here. And that register is also a shift register. As bits come in, they enter in and they move out like that.
Okay, so this shift register is where?
Is on the
receiver
on
that side. Okay,
this is a receiver side shift register. In fact, we can, just to make it simple, we'll call this the transmit FIFO.
Okay, just so you're not too confused.
I'm not confused. So this is on the receiver side, and this guy also has a clock associated with it. Right? There's a clock that controls it. Okay. Now, why do I need a clock, John?
Okay, because you're shifting, right?
Yes.
Because every time you get a clock pulse, you shift the shift register.
Yes, and that tells me at what rate I move the bits into my shift register. That clock drives it. And these two clocks should be at the same rate, which is what we call as the baud rate. And which we'll talk about this more in some more detail later.
So we got to shift them at the same rate.
Exactly. So we get data. Eventually this data...
Okay, how big is this shift register?
So this shift register is also 10 elements.
Oh, okay.
Right? It's also 10 elements. Again, it has the same format. Our start bit shifts up and comes here. Eventually our stop bit comes here, and that's our stop bit.
Okay.
Now when we put this into our FIFO, it's a little more complicated on the receiver side. We'll see why, but the details are almost the same. There's a receive 4-element FIFO.
So is this hardware or software?
It's all in the hardware.
Oh, nice.
These are hardware FIFOs, right? This is a hardware FIFO. And and it's implemented within that module. So this one eventually will come out, and then it'll go into a register. We'll call this the RX data register.
Okay.
And
Okay, now is the start and stop bit still in the RX register?
yeah, so that's what we need to do. We need to figure out what exactly goes into our RX data register, right? So it turns out that we need all of this data to be here, right? But we only need the payload, which is the payload, which is our 8 bits. So RX data should have the 8 bits in it.
Okay. So even though the frame was 10 bits, these two data
Exactly,
registers are
because
only 8 bits wide.
This is 8 bits go, 8 bits come.
Yep.
Right? We need
Got
only
it.
8 bits there, right? So these things come. Now, in a system like this, there are possibilities of errors. So in fact, there are other error bits that are added.
Ooh.
The error bits that are added have to do with something called parity error, a frame error, a bit error, and an overrun error.
Got it.
So you learn more about those somewhere else. But the system, the receiver computes those error bits and then puts them there. So those error bits are available to us if we want to see them. But that's besides the point. But at the end of the day, I want 8 bits coming out here, right? So I get my 8 bits. So now what should my reading strategy be here? Well, there has to be a flag that tells me if there is any items to consume, right?
Okay.
So it is called a receiver FIFO empty flag.
Oh, I see. So if the hardware FIFO is empty,
Then there's nothing to consume.
nothing to consume. I get
So
it. Good idea.
if nothing is consumed, so I'll check that flag called the RX FIFO empty flag, and if that flag is a 1,
Okay, that means
there's nothing to consume.
that means it's empty.
And
Okay, got
so
it.
I'm gonna busy wait and go keep checking that flag.
Got
If
it.
I do have something, I'm gonna read and return. If this is subroutine, I'm just gonna read and return what is in RX data.
Now, what happens to that receive FIFO when I read it? Is it still there?
So as this is once I take an element out, as soon as I read it, the next element from this FIFO moves down, and it's a first in first out. That's the key point here. That is, the first element that entered the FIFO is the first element that exits it. The first one that entered the IO is the first element that's going to leave.
Okay, so it's order preserving.
Order preserving.
Oh, sweet. Cool.
So that's the internals of our FIFO.
Good.